Okay, good. So in this one, we are going to learn how to define a custom function in Mathematica. So let's consider an example of plotting multiple functions. So here I have three functions, f being 2x squared, g being 5 times x squared, and h is 10 times x squared. Now I want to plot these functions. So in that case, I will have to define each of them one by one, and then I will use the plot function to plot them like this. But to do this, we had to define three separate functions, and that is not an efficient way to do it. So if you look at these functions, they are of similar form. They are actually a times x squared, where a is 2, 5, and 10. So in this case, we can define a general function, that is f equals a times x squared, and then call it whenever we want. So we will define our custom function called f. So currently f is defined as 2 times x squared. To check what f is, we simply use question mark f, and this gives us. Okay, good. So in this one, we are going to learn how to define a custom function in Mathematica. So let's consider an example of plotting three functions. So we have here f equals 2 times x squared, g is 5 times x squared, and h is 10 times x squared. So if you want to plot these three functions, we will first have to define them one by one and then plot it as fgh, where x is running from -10 to 10. And when we plot that, we get something like this. But this is not an efficient way to plot these three functions. We should actually define a general function such as f equals a times x squared, and then change the a from 2, 5, and 10. So I want to call this custom function as f, but currently f is defined as 2 times x squared. So if you want to check information about any variable, just put question mark f, and then Mathematica gives you information about that variable. So here we have f as 2 times x squared. So I will clear f, and now I will define our custom function f being a times x squared. So we have two variables. They are defined like a underscore and then x underscore. After that we have colon equal sign, and then goes our function. So it is simply a times x squared. So this is the method to define a function in Mathematica. You will have the name of that function, then the variables of that function, and then colon equal sign, and then the mathematical form of that function. So when we define this, we have f defined as a general function of a and x, and then I can perform the same task of plotting fgh. So instead I will have f of 2x, because f was 2 times x squared, and then g is 5 times x squared. So I will have g as, so we can represent g now as f of 5 comma x, and then h as f of 10 comma x. And so this should plot the same graph as above, and we get exactly same plot. So defining a custom function is really useful. You don't have to have multiple lines of different functions. That also takes unnecessary use of variable names and then multiple lines of code. So all this can be done by defining a single general function like this and calling it again and again in our plot function. We can also find the value f takes for maybe when a is 1 and x is 4. So I will just put f of 1 comma 4, and it should give us 1 times 4 squared, that is 16. So this was a simple example for defining a function. Now I want to define something little more complicated, such as a Gaussian function. So if you're not familiar with a Gaussian function, it looks like a bell curve. We will plot it soon, and we can see we have multiple variables here. I can count them as sigma, x, and mu. So to define this function, I will write Gaussian of sigma underscore, then mu underscore, and then x underscore. So these are my variables, sigma, mu, and x, then colon equal. And now we will have to type in this form of function. So let's do it. Sigma times square root of 2 pi, and then we have exponential function. It goes like 1 over 2, and then we have x minus mu squared, and it is divided by sigma squared. So once we define this general form of Gaussian function, then we can use it for different values of sigma and mu. Know that the sigma represents the spread of this curve and mu represents the location where peak of this curve will appear. So I will define it, and now we can plot this function like Gaussian of, let's take sigma to be 1, mu to be 0, and then x, where x runs from minus 10 to plus 10. So let's plot it quickly. So here you can see Mathematica is not plotting it fully. So in such case, where your curve is cut off along some axis, you should use plot range all, and then we get the complete curve here. So as I said, mu of this Gaussian function is at 0, so this curve is centered at 0, and the spread of this function is 1. So along with this Gaussian function, let me plot one more Gaussian function with a higher spread. So you can see we have first Gaussian here and the second Gaussian within curly braces, and x is going from minus 10 to 10. We get two Gaussian curves. We just saw the blue one with spread 1, and now we have new Gaussian in orange having larger spread of 2. Let's also plot a Gaussian function in 3D. So for 3D Gaussian, we just have two exponentials along x and y direction multiplied with each other. So we will write Gaussian 3D. It's a function of course, x-axis and y-axis, and then it will have spread along x as sigma x. Don't forget the underscore. Then we have sigma y underscore, then mu x underscore and mu y underscore, and then colon equal. As I said, we will have product of two exponentials, so I will just copy this exponential here, and then we should change this mu to mu x and this sigma x like this, and this is mu y and sigma y. Here it should be y, and so this is our 3D Gaussian function. Let's define it and then we will plot it in 3D. So I hope you recall plot 3D from previous lectures. So first we have a function like this. The coordinates are x, y. Then I want sigma x to be 1. So the spread along x-axis is 1 and the spread along y-axis is also 1. And the location where the center or the peak lies, let's take it to be 0, 0. And now x runs from minus 10 to plus 10 and y runs from minus 10 to plus 10. So plot it, we get again incomplete graph because we forgot plot range to all. Let's also add axis label. So we have three axes x, y, z, so I will simply call them like this and evaluate. We get a nice 3D Gaussian plot like this. We can increase the spread across one of the axes like this. Let's take it 3. So now this Gaussian plot should have higher spread along x-axis. So let's evaluate. And you can see along x-axis it is having much larger spread as compared to y-axis. Let's take 3 in the both axis, and let's also change the location to maybe 2 2, and so you can see it is not in the center anymore, it is shifted to location 2 2. So yes, this is how you define your own function in Mathematica. You can use this method to define even complex functions. I recently used it for one of my works on Lagrange Gaussian beams. For that I had a much more complex function like this here, this W. These are complex weight factors corresponding to a light beam called as Lagrange Gaussian beam, and I define it like this here. So you can see there are so many variables involved, and I call this function multiple times by changing this lm lambda parameters, and later on I use them to plot for different cases of m being 0 plus 1 and minus 1. So defining your own function becomes very useful sometimes, and I hope this lecture helped you in understanding that. So with this much, I'll see you in the next one.